Hey everyone! Have you ever used a compass and wondered why that needle always points north? Or maybe you've seen a crane effortlessly lifting heavy metal using just a magnet? Well, that's magnetism at work, an invisible force that's everywhere around us. Magnetism isn't some abstract physics concept confined to a lab. It's something we experience daily, from refrigerator magnets sticking to the door to those magnetic locks on your hotel room, or even the metro card readers that you swipe every morning. The source of all this? Moving electric charges and the tiny magnetic moments of particles like electrons. This is the essence of magnetism. Now, here's the kicker. Earth itself acts like a gigantic magnet. It has a magnetic field extending from the south geographic pole all the way to the north. Ever wondered how a compass works? It's because of this magnetic field that points north, making navigation possible. Pretty cool, right? But not all materials interact with magnetic fields the same way. Depending on how they respond, materials are classified into three main types: ferromagnetic, paramagnetic, and diamagnetic. For example, materials like iron are ferromagnetic, which means they are strongly attracted to magnetic fields. On the other hand, diamagnetic materials like graphite slightly repel magnetic fields. It's fascinating how everyday materials react to this invisible force. So, to wrap it up, magnetism is all around us. It's in industrial cranes, in the orbits of electrons, and even in the magnetic compass guiding you through your next adventure. Today, we've just scratched the surface, and we'll dive deeper into how this force shapes the world around us. Stick around, because magnetism is more than just a science lesson. It's a force that moves the world. Let's dive into a fascinating topic today: Earth's magnetism. Now, you might have heard that the Earth acts like a giant magnet. But have you ever wondered why? Let's find out. Imagine standing outside on a calm day and you hold a compass. The needle points north, right? That's because of the Earth's magnetic field. This magnetic field is generated by the motion of molten iron and nickel in the Earth's outer core. It's almost like the Earth is creating its own magnet right inside its core. If we think about the Earth's magnetic field, it actually resembles that of a bar magnet. Now, here's the interesting part. The Earth's magnetic field is tilted by about 11.3 degrees with respect to the planet's rotational axis. It's almost like the Earth's magnetic field is leaning slightly to one side, just like tilting a bar magnet. Let's take a look at this image here. Notice how the magnetic axis, that's the line running from the magnetic south pole to the magnetic north pole, doesn't perfectly align with the geographic axis, which connects the Earth's north and south poles. This difference leads to what we call magnetic declination. Magnetic declination means that the direction of magnetic north doesn't exactly match the geographic north. It's shifted by a few degrees depending on where you are on Earth. Now, let's talk about magnetic inclination or dip. This is the angle formed by the Earth's magnetic field and the horizontal ground. In other words, it tells us how steeply the magnetic field lines are slanting as they enter the Earth. So, to sum it up, the Earth's magnetic field is not just a fascinating natural phenomenon, it's also a powerful tool we use every day with compasses, navigation, and even understanding the planet's inner structure. The way the magnetic field is tilted and interacts with the Earth's surface plays a huge role in guiding us and protecting us. I hope you now have a deeper understanding of Earth's magnetism. See you next time, where we'll explore more exciting scientific concepts. We are now going to talk about something that's around us all the time but often goes unnoticed: Earth's magnetic field. Specifically, we'll explore declination and dip, to important concepts that help us navigate and understand the direction of the Earth's magnetic forces. Now, have you ever used a compass? It always seems to point north, right? But have you ever wondered exactly why it does that? This brings us to declination. Declination is the angle between the magnetic meridian, the direction that a magnetic compass points, and the geographic meridian, which is a true north-south line. In simple terms, it's the difference between the direction that your compass needle points and true north. And then we have dip. You may have noticed that sometimes your compass needle doesn't just point horizontally, it may tilt. This tilt represents the dip, or the angle the Earth's magnetic field makes with the horizontal at any given point. Essentially, the magnetic field is not only pointing in a horizontal direction but also tilting towards or away from the Earth's surface. As you can see in the diagram, declination and dip both vary depending on where you are on Earth. The geographic location plays a key role in determining these values, and this is why navigation using a compass can be tricky in some places. In fact, it is critical to understand these values when navigating, especially in unfamiliar territory. For example, did you know that at the magnetic equator, the dip is 0 degrees, meaning the Earth's magnetic field is parallel to the surface? On the other hand, at the magnetic poles, the dip reaches a full 90 degrees, the magnetic field is pointing straight down. So, as a quick recap, declination is the angle between magnetic and geographic north. Dip is the angle the magnetic field makes with the horizontal. Both of these values change depending on where you are on Earth, and they are crucial for accurate navigation. I hope you now have a clearer picture of how Earth's magnetic field works and how important declination and dip are in navigation. See you next time when we dive into another exciting concept of physics. Now, let's talk about magnetic intensity, symbolized by H. Magnetic intensity is the strength of the applied magnetic field, and it is independent of the material properties. Imagine it like the pressure you apply when pushing a sponge. The force doesn't change based on what the sponge is made of, but the sponge reacts to that pressure in different ways. In the same way, H is the strength of the magnetic field applied to the material. But here's the cool part, materials don't just sit in the magnetic field. They respond to it. The total response of a material to the magnetic field is captured by the formula B equals mu naught into H plus M. Here, B represents the total magnetic field inside the material. Mu naught is a constant that represents the magnetic permeability of free space, and H and M are the magnetic intensity and magnetization, respectively. This formula shows how both the applied field and the material's magnetization combine to create the overall magnetic field. It's like how the effort you put in and the material's natural properties combine to give you the final result. So, whether it's your refrigerator magnets or the magnetic compass guiding your way, these properties play a huge role in how materials interact with magnetic fields. I hope this helps you understand how magnetization and magnetic intensity work together to influence the magnetic world around us. See you next time as we explore more fascinating concepts in physics. Do you know how a simple bar magnet works? It's fascinating. A bar magnet produces a magnetic field similar to the Earth's magnetic field. The field lines emerge from the North Pole and loop around to enter the South Pole, forming a closed loop. You can think of it like the way the Earth's magnetic field surrounds our planet, guiding compasses and creating magnetic forces all around us. Now, the strength of this magnetic field isn't the same everywhere. It's strongest at the poles, where the field lines are most concentrated, and it gradually weakens as you move away from them. Imagine a flashlight. When you're close to the beam, it's brightest, but as you move away, it dims. That's the same idea. And here's where it gets more interesting. The strength of a bar magnet's magnetic field can be quantified by the magnetic dipole moment, which is given by the formula m equals m into 2L, where m is the magnetization and 2L is the length of the magnet. This formula helps us understand the strength and reach of the magnetic field that the magnet creates. So, whether you're using a compass to find your way or just playing with magnets, you're interacting with the invisible yet powerful force of magnetism. Isn't it amazing how something so simple plays such a crucial role in our world? So, the torque acting on the magnet is 0.0173 N.m. This torque is what causes the magnet to rotate when it's in a magnetic field, and it's the same principle behind how electric motors work. I hope this makes the concept clearer. Keep exploring, and I'll see you next time for more exciting physics. Have you ever wondered how magnets work or why Earth seems to have this mysterious magnetic field? Well, it's all about magnetism, a fascinating force that arises from moving charges and the magnetic moments of particles. Let's break it down. Magnetism is created when electric charges move. Picture this: whenever an electric charge moves, whether in a wire or at the particle level, it creates a magnetic field around it. This is exactly what happens with electrons as they move, giving rise to tiny magnetic moments, and this is the fundamental cause of magnetism itself. Now, let's zoom out and think about Earth. Did you know that Earth itself is like a giant bar magnet? It has a magnetic field that stretches from the South Pole to the North Pole. This magnetic field is what makes compasses work. And there's more. There are special angles like declination and dip, which affect how compasses behave. It's a pretty neat way that the Earth guides us in the right direction. So, to sum it all up, magnetism is all around us, from the magnetic field of the Earth itself to the magnets we use every day. It's a force that not only shapes our physical world but also helps us navigate it, making it an essential part of both nature and technology. See you in the next lesson, where we'll uncover more secrets of the universe. But not all materials react to magnetism the same way. Some materials, like iron, are strongly attracted to magnets. These are called ferromagnetic materials. Others, like wood, don't interact with magnets at all. These are diamagnetic. And then there are materials like aluminum that fall in between, which are called paramagnetic. All these materials react to magnetic fields in different ways because of properties like magnetization, magnetic intensity, and permeability. And then we have bar magnets, the ones you use in experiments. A bar magnet has two poles, north and south, and a magnetic dipole moment. When a bar magnet is placed in a magnetic field, it interacts with that field, producing torque, which is a force that causes the magnet to align with the field. It's like the magnet can't resist turning to face the direction of the magnetic field.